Alright, let's do a quick recap on the photoelectric effect. First, we highlight the experimental setup. Right? It involves a cathode and an anode. The cathode is where the metal is connected. It is where the light is shown, and it is from this cathode that the electrons would emerge. And in this instance, right, we've connected the anode to a negative potential. Right? So it is actually at a lower potential compared to the cathode. The presence of the ammeter in the circuit is there to detect the photocurrent. Now, let's work from first principles. If you have the cathode over here, let's call it C, alright, and the anode on the other side, let's call it A. We know that since the anode is at a lower potential compared to the cathode, an electron, right, within these two plates would experience a force, an electric force, towards the left, right? So as this electron moves from the cathode to the anode, right, its displacement is towards the right. So the work done on this electron, right, is given by the force, electric force on the electron multiplied by its displacement. Now, we know that within this, there is an electric field that is set up. So the electric force, right, is actually given by the charge of the electron multiplied by the electric field strength multiplied by the displacement. Now, we also know, right, recall that if we consider the electric field between the cathode and anode as a uniform electric field, then the relationship between electric field strength and potential difference across the plates is given by this, right? So we can replace E times delta S, right, with delta V. Overall, right, we know that this work done on the electron is going to be negative. Reason being, direction of force on the electron is towards the left, direction of displacement of the electron is towards the right. For our purposes, we're not concerned, right? We'll just take the absolute value. Now, if the work done on the electron is negative, right, that means that the electron will slow down as it moves from cathode to anode. So the Ke of the electron decreases. By conservation of energy, right, that means that the potential energy of the electron must increase. Right? So if we were to write down an equation, right, using conservation of energy, we have that the total energy, right, at the cathode, let's call it Kc, plus potential energy at cathode, Uc, must be equal to Ke at anode, plus potential energy at anode. Okay. So we can rearrange this expression, right, so that we bring all the kinetic energies to one side, and all the potential energies on the other side. And you see that essentially this says that the decrease in kinetic energy is equal to the increase in potential energy. There's a relationship between potential energy and work done, right? And that is simply that that increase in potential energy is due to the work done on the electron. So this is a relationship that is true, and it is true in general. And we will use this relationship to help us to obtain one of the very first expressions that is important for us. Now, come back to the experimental setup. Right? So what this is saying is that the decrease in kinetic energy of the electron as it moves from the cathode to anode is given by the absolute value of the electric charge multiplied by the potential difference across the cathode and anode. Now, if we increase the potential difference across the cathode and anode, right, what will happen, right, is that the kinetic energy of the electron at the anode would decrease. There will come a point of time, right, when we have increased the potential energy to such an extent, right, that the kinetic energy of the electron at anode is equal to 0. Now, when that happens, right, we then have our first relationship. Okay, so So I'll write down the other one, the general relationship for reference. Right? So KE at cathode minus KE at anode, right, equals to E times the potential difference. Right? So I said this is a true relationship, right? It's true, applies in general. So I said that if we increase the potential difference, right, across the cathode and anode, what will happen to the KE, right, at the anode is that it will increase. So there will come a point of time which we define as the stopping potential, right, where the KE at A becomes 0. Right? So what we have then is that kinetic energy at C that equals to E delta V, and we call that stopping potential. Now, this helps us to obtain this relationship. Right? So the K at C then is what we call the maximum KE of the photoelectrons. Right? So this is a relationship that is important. K max, right, equals to E times delta V. Now this is a very important relationship, right? And I hope that the discussion of how it's derived from first principles was helpful for you in understanding how this comes about. Okay. So let me put this in a red box. Right? This is important. Now, the next important relationship involves the conservation of energy. Right? First of all, let's understand the definition of the work function. The work function is the minimum amount of energy that's required to remove an electron from the metal. Right? So if light falling on the metal plate has energy of HF, right, then if we take away the minimum amount of energy that is required to remove an electron from the metal, what we're left with is essentially the maximum KE of the photoelectron. Right? So this is just simply a statement of conservation of energy and is another important relationship. Right? So I'll put that again in the red box. Now the third important relationship comes from combining these two relationships. Right? So essentially what we'll end up with, right, is this. Right? So E times the stopping potential equals to HF minus the work function. I forgot to mention, all right, that because there is a relationship you recall from year 4, right, V is equals to F lambda. So therefore, right, HF is also equivalent to HC over lambda, right, where C is basically the speed of light. Right? So depending on what information is given to you, right, HF or HC over lambda. Now, back to this equation here. If I divide this equation throughout by E, right, what I end up with is this expression here. This expression, I hope you will recognize, right, is in the form y equals to mx plus c. Means to say that if I have a graph, or if I plot a graph of stopping potential, right, stopping potential versus frequency, right, what I expect to have is a straight line graph of gradient h over e and vertical intercept minus phi naught over e. So my vertical intercept will be minus phi naught over e. Now, what about the horizontal intercept? When V stop, or when the stopping potential is equal to 0, recall that there was a relationship between maximum KE and E times V stop. So when V stop is equal to 0, that corresponds to the horizontal intercept over there, it means that the maximum KE of the electrons is 0. It means there are no electrons that come out, right? And so mathematically, if we put V stop as 0, right, we have that 0 equals HF minus phi naught. So F at that point is given by phi naught divided by h. Now, because there is no photoelectrons emitted at that point, we can say that this is actually the threshold frequency. So the horizontal intercept in this graph is actually the